In position 1 in the figure, the spring constant K is undeformed. So right here means delta X, displacement from equilibrium, is 0. Find the work done by force F, which is always directed along the tangent to the smooth hemispherical surface on a small block of mass m to shift it from position 1 to position 2 slowly. And the word here, slowly, is a key word to your phrase. Basically means that when you're doing energy balance, you don't have to take into account kinetic energy because it says that V is small, therefore energy kinetic, which is 1/2 mv squared, is kind of sort of 0. So that's all that means when you see it moving slowly or repositioned slowly. That's what that means. All right, so concept going on here. We draw a picture. I'm going to use the one that they have drawn here because it's a good picture. This is position 1. This is position 2. Seems reasonable. I should really redraw it. I know, you're right. First step, every physics problem, draw the picture, often redrawing it. In this case, redrawing it poorly. So what I'm going to do here is I'm going to say block starts here. This is 1. Block ends here. This is 2. This is, I'm going to call this, they call it theta. I'm going to call this theta final. Just because it makes sense to me to start at one theta and end at a different theta. And the idea here is we've got a spring. Yep, same picture, and then I'm going to call this distance radius r. They use a, I'm going to call it r. We'll translate it at the end to make everything match up. Okay, so I'm going to start with the concept that work equals integral f dot dx. Where these are both vectors, and that's a dot product. Dot product is just a measure of how parallel two vectors are. And I'm going to break this force up into two components. So I'm going to say that this is integral force due to gravity, because we have our block here, and there's two forces acting on this block. We have force gravity, and we're going to have force spring. There's no reason that the spring is off-centered like that. It's just so I can write it easily on the same block. So force gravity dot dx plus integral force spring dot dx. And I can add these two together like this because these are both scalars. When you take a dot product of two vectors, you end up with a scalar, which is work, which is just a measure of joules, or electron volts or other kilowatt hours, maybe? I don't know. Energy. And so we have the work due to the spring, work due to the gravity, and I'm going to add them together. I'm going to make everything positive because both gravity is acting down and spring is acting down. So I'm not going to care too much about the nuance of the signs because I know that they're all going to act in the same direction. So I'm going to start by looking what force gravity is. Force gravity is going to be mass times gravity. But this is a dot product, and as we get bigger, the distance of travel is going to be this way. Gravity is going to be down. And so even though they start parallel down here at the bottom, or I guess anti-parallel, similar direction, I'll say parallel. Because really we're concerned with finding this force, so what we're going to do is we're going to find the negative of it. You'll see where it goes. So they start at maximum and then they go to minimum. That is going to be represented by cosine theta. So when we start in the beginning, so I'm going to do this from x initial to x final, where x initial is right here, x final is right here. I know I'm probably explaining this the most confusing way possible. Bear with me, it'll all come together. Maybe, hope so, we'll see. Mg cosine theta. Yep, so as it goes up, the work done by gravity decreases because you're not going straight up anymore. You start by going straight up and then you're kind of going in angles. Mg cosine theta. Normally think of dot products. I actually do think of dot products as cosine, so I'm good with that. And that's why I think of dot products as a measure of how parallel two vectors are. Some people memorize that it has to do with cosine theta, but then you have to be like, well, which theta are you actually talking about? So that's why I try to reason that out when I can. So force spring is kx. It's k delta x, negative k delta x. And the negative just means that it's in the opposite direction of displacement. But since we know that everything, gravity and spring force are acting in the same direction, that's going to drop the negative, because all it tells us is direction. In this case, though, we're going to say that we start at 0 here. X equals 0, so this delta x is just going to be the same as kx. Yes. And I think we can write this out now. So I'm going to say that we have the integral mg cosine theta. I'm going to do dx plus integral kx dx. All right. So now it's going to be easier to integrate this with respect to theta instead of x. So we need to find a relationship between x and theta. So I'm going to draw myself another picture here. I should do a different color so that I can show the change in thought process. So this arc length right here is our distance traveled. These are our radii r, which are the same radius, and this is theta. Therefore, I'm going to say that x, our arc length, equals r theta. And specifically, for a small bit of x, we're going to use a small bit of theta. And then go from delta, which is a small little bit of change, to an infinitesimally small change. We get dx equals r d theta. And if you used polar coordinates before, you're kind of like, oh, this feels almost familiar. So we're going to go with that. So substituting things in, this is going to be work total. This is going to give us, actually I don't have to use an arrow, I can say actually equals integral mass gravity cosine theta dx is r d theta plus integral k, which is a spring constant, x, which we know is r theta, times dx, which we know is r d theta. Rearranging this, I'm going to do each of these individually because I can. Mg integral cosine theta mgr d theta plus k r squared integral theta d theta. And now our limits of integration here are going to be from theta 0 to theta final, theta 0 to theta final. And we need to figure out what those are. So when x equals 0, theta is also going to equal 0. When x equals x final, we're going to have theta equals theta final, which in the problem is actually denoted by theta initial, but we're going to worry about that later. I'm just going to go with by notation because I prefer it. But you're right, it's a good catch. All right, so yes, going to integrate these. mgr, the integral of cosine theta is positive sine of theta, plus kr squared, because those are constants, theta squared over 2, power rule. This is all going to be integrated from theta initial, which is 0, to theta final. When we plug 0 in here, sine of 0 is 0, theta squared of 0 is still 0. And so this part doesn't matter. We just plug in theta final. So we're going to have mgr sine of theta final plus kr squared theta final squared. That's a terrible squared over 2. Yes. And that is basically going to be our answer, but we're going to have to translate it into what they wanted for their initial conditions. Is that right? Yeah, that might be the entire problem right there. All right, so now I'm going to copy and paste this real quick just to make sure I get what they want. So this is going to be work total equals m times gravity, which we're allowed to say gravity is g. R, though, they say is a, sine theta initial, because they use theta initial, plus, and they use a big K, I use a lowercase k, doesn't matter, a squared, which happens to also look like a 2, but I can do a better job, a squared, and then theta initial squared over 2. And this would be what I think would be the final answer for this question. So to recap what we did real quick, because it was kind of crazy, we had this mass that moved along basically a circular arc, and we attached a spring to it, and we want to find the work done to pull it that way. So this work, we use the idea of work equals integral f dot dx. It's an integral of force along direction of displacement, dot product. And we broke that up into part due to gravity, part due to spring constant. We then wrote everything out in terms of x. We then looked at it like, all right, this will be easier to solve in terms of theta. So we looked at arc length, x equals r theta. We then looked at the derivative of each. The small bit of change in x is r small bit of change in theta. We changed our limits of integration, plugged those in, did some pretty reasonable, straightforward calculus, got an answer. So this problem, 90% set up. Once you understand how to set this up, not too bad. So hope that helped. See you next time.